Okay, welcome back. Guys, yeah. I think we should start, otherwise we're going to be late again for lunch. Okay, so we have today instrumentation part 2. Ada is going to show us a little bit more what's inside LISA, because she's a big part of the instrumentation team. She's from the Albert Einstein Institute in Hanover, in Germany. And yeah, go ahead, Ada.
Yep, thank you. Thank you for having me here and having this opportunity to talk about the LISA hardware. And I would like to encourage you to ask as many questions because so sit back, there's going to be lots of pretty pictures, but ask lots of questions. And there's lots of acronyms, there's a lot of stuff. So, yeah. And I want to start with a little bit of recap what Henri was saying. So on the LISA measurement concept, as Henri already said, what we want to do is we want to provide the measurement of a test mass to test mass distance. And in our world, it splits into a couple of the few of the measurements is the, I will get used to it, is the measurement between the optical bench to the far spacecraft and from the optical bench to the test mass on each sides. And this is the primary objective of the system called optical metrology system in LISA. The secondary objectives is to provide a constellation tracking. And as we know, we have to suppress laser frequency noise because, as Henri mentioned, we're more or less 8 orders of magnitude higher than the signals that we want to measure. So how do we do that? We measure it directly by measuring the phase of the laser beam of the heterodyne beat node. And this manifests as, so we have the incoming laser light, our RX from far spacecraft, and we have a local oscillator from the local laser. We beat those two against each other, and what we actually measure on our detector is the difference in the frequency. Once we have the gravitational wave that imprints the phase modulation of that light, this is maintained on our beat node, and to some extent enhanced because we are now having shorter wave. This displacement that we want to measure is directly proportional to phase. And as we see, since we wanted to measure of the order of tens of picometers, that's also of the order of tens microradians signal. So each LISA spacecraft works as a transponder. It doesn't send light back because we are receiving only picowatts out of a 2-watt laser. So we have to lock to the incoming laser beam and send it back. And that we create 6 links in the constellation. So the important part of here is what we want to measure is that we want to measure the phase shift of the laser beam. Now, did I already have that one? Yes. So what is challenging here is first thing is that we have unequal interferometers. So we have to add them up in post-processing. As I already said, we have 6 links. We have dominating laser frequency nodes we have to suppress. For that, we use TDI techniques. And to support TDI techniques, we have to also provide another functions, which I'm going to be talking about in a second. And the big challenge here is that due to the Doppler shifts, we are measuring in a megahertz regime. What is difficult for electronics is that we have to have much better clocks to actually take and measure these frequencies. And clocks that are precise enough and space-graded are not readily available. I mean, they exist, but they are more or less size of 2 of those desks. They are very heavy, and they're cryogenic. So that's no-go for space application. Therefore, we have to play some tricks, exchange the clocks, and correct of all the jitters of our clock. So each LISA spacecraft has its own clock, and they drift, which means that, for example, one of the spacecraft will consider the other spacecraft's second a bit shorter or a bit longer. So, as I mentioned, we have to suppress laser frequency noise. using TDI techniques, and for that we need high-resolution timestamping of the phase measurements, so to ensure that all of the measurements are consistently timestamped and marked as with high precision, because what we are getting is we're getting phase and time readouts, so tables. We want to know the absolute distance of the spacecraft up to 1 meter. We have to exchange our timing reference between spacecraft to use it in post-processing and synthesize our virtual clocks that we share into one common reference for all of the measurements such that we can later reference it to any meaningful data, what we want to observe as the gravitational waves. So for that, our optical metrology system consists of following instruments. We have a LISA laser, which I'm not going to be talking much about it. It's a very special laser developed by NASA. As you know, it delivers 2 watts of power, but actually what we read on the other side is around 400 picowatts. We have LISA telescopes, which I'm going to mention a little bit about. They are also developed by NASA. We have optical bench that hosts our interferometers. We have phase measurement system that is not really present here, except the detectors that are sitting. We consider the test mass surface a part of OMS because we have to reflect our light from something, although this is really the GRS, so ground reference sensor system that is provided by Italy, Trento. And our MOSAs, to close the link, they have to exchange light and provide the reference for each other. So since I mentioned that some of those parts already are delivered by NASA or by GRS, what I'm working on is, and I lost a slide. Yeah, that one. It was supposed to be bold and visible. So what I'm working on is the so-called interferometric detection system. It's actually a system that is being delivered by European contributors, and I will mention where each unit is coming from. And we are providing the system engineering to ensure that it all works together and is going to provide all of the data, all of the science that we need. And that consists of the optical bench and all of the units that are sitting on it, phase measurement system, including LISA phase meter and detectors, as well as interfaces and other bits and bobs that we're going to talk about today. So as I mentioned, interferometric detection system consists of optical bench assembly. It hosts the quadrant photoreceivers and 3 units that support constellation, noise reduction, and redundancy. We have 2 boxes that are actually LISA phase meter sitting here. We have the box that controls our units because we have to make sure that we maintain constellation. And we have to interface with, as I already also mentioned, with other systems in the LISA world. So we have 3 interferometers. We have science interferometer, which is the TX light that comes from the local laser and is beat against the RX beam coming from far spacecraft. That is one of our scientific measurement. We have test mass interferometer, where we have the local TX beam that is picked off and is retroreflected from the test mass, and it beat against the beam that comes from the adjacent optical bench. And then we have also reference interferometer, that is the TX beam sent directly and this local oscillator that comes from the adjacent bench. Yes.
Is the science interferometer the same thing as is usually referred to as interspacecraft interferometer?
Yes.
ISI?
It has multiple names: long-arm interferometer, interspacecraft interferometer, and currently science interferometer.
Okay.
Just to confuse everyone.
Okay, and those are the only 3 interferometers, or?
Yes.
Okay.
Those are only 3 interferometers that we have on and we measure.
6 of each, right?
3 on each optical bench, 6 on one spacecraft, times 3 spacecraft.
Okay.
So those three interferometers on each spacecraft allow us to close the link and provide the linear combination for TDI. So, as I mentioned, I work on the interferometric detection system, and we have to also provide other functions apart from the phase measurement, which, as I already said, clock distribution, pseudo-random noise ranging to provide the absolute distance between spacecraft. We need to support reduction of a noise because RIN, for example, is a big problem for us for those light levels of picowatts. So we have to reduce the noise, also reduce the stray light noise that comes from the telescope or other sources on the optical bench. So we provide technique called balance detection. We need to support tilt-length coupling suppression. We have to correct for pointing. As we know, it takes 8 seconds for LISA to light to travel. So we actually have to point where the spacecraft will be in the future, not where it is right now. We also support function. I'm not going to be mentioning this one too much, the intersatellite data link transfer. So at any given point in time, we're going to be talking only to one satellite that is going to be the closest to Earth. Therefore, we cannot download data from other satellites, right? We'll have to wait until the other satellite shows up, and then we talk to it. To bypass this, we send all of the data to one spacecraft that is going to be talked to on the next the session from the operations center. So we have to support this as well as it's one of the phase emitter functions. We have to control the laser to maintain transponder locks, and we have to acquire bit nodes. So initially, the spacecraft are in space, and they now have to acquire bit nodes and start measuring. We also have to provide lots of redundancy because in space, we cannot just go there and fix things, so we have redundancy upon redundancy upon redundancy to make sure that everything works for a given time that is being promised. So, okay, that's the intro.
Just on that note of redundancy, do you have more? I mean, you're saying you're going to choose one satellite as the hub,
Yes.
which you'll always talk to at any time, right?
Mm-hmm.
It's one of those three. Like, where's the redundancy for that? Don't you need to?
So each of them has high power antennas. This is actually being developed by the prime contractor, which builds the whole satellite. And I'm not entirely sure if there's going to be multiple antennas or I'm pretty sure there is redundancy in that. But you can also consider that even if there's a failure, you can always talk to the next satellite because they all have all of the data from the measurements.
Ah, okay.
Sorry, so you mentioned a spacecraft. Did I, like, you said, so yeah, so there's a spacecraft that's who's on it, who's, or whatever. Its only job is to acquire data? Is that, did I understand correctly?
No. So each spacecraft measures its own data.
Sure.
Each has its own phase meter that measures data. But we only talk to one satellite at a time.
Mm-hmm.
So we would only get the data from that satellite.
Okay.
Yeah, I think there was a question there as well.
So you mentioned a point ahead effect, right? So is that one related to or is the same as what he introduced as beta H term? No?
No.
Okay.
Did you?
Say that again. Say your question again.
So there's a point ahead effect, but is that effect the same as what you mentioned as a beta H term?
I guess it's the fact that you need to point towards the distant spacecraft, but accounting for the fact that during the light travel time, the spacecraft is going to move. So you need to anticipate the motion of the distant spacecraft until it receives the laser beam.
Okay.
I think that's what it is.
In a way, it is the same. In the space-time diagram, this is that the geodesic will reach the emitter at the time
It's not
of
a
emission.
beta H effect.
It's just beta, yeah.
Yeah.
So it's the same.
It's the beta.
It's a beta. It's due to the beta, the fact that your receiver is going to move during the light travel time. Indeed.
Okay, so let's jump in. So the first in the chain, we have LISA telescope. As I mentioned, LISA telescope is developed by NASA. It's being tested at the University of Florida for its dimensional stability. Everything in LISA has to have absolutely amazing dimensional stability. This is how it looks. This is a picture from NASA of the telescope with this beautiful gold-coated primary mirror. So the requirement on the stability between the primary and secondary mirror for the whole measurement is picometer per root hertz, in-band stability. And this is very tricky. Therefore, this whole telescope is built from the zero door. It's this low thermal expansion glass that is maintains stability in the various temperature ranges. Telescopes can be exposed to environment as well because it's the one that looks into it. It also has to ensure that the path length across this primary mirror is maintained across the wide field of view, and it also needs to minimize the backscatter from its mirrors to the optical bench and further to the detectors, because that generates the noise. So not going to be talking much about it because it's not part of our European contribution. So let's jump further into optical bench. I'm going to walk you through optical bench in a second, but its primary objective is the host interferometers and interface with and exchange light with various units, host quadrant photoreceivers, provide tilt-length coupling compensation by well-aligned its optics and its units, such that we minimize geometrical effects, as well as host the so-called beam alignment mechanism to compensate other geometrical effects also coming from a telescope, because this whole coupled system, as I mentioned, provide point-and angle mechanism and necessary redundancy. So this is the optical bench. This is A side. It hosts the science interferometer or longer interferometer. And as you can see, it's this big yellow blob, which is the zero-door baseplate. Again, we need to provide very good stability. If the bench is going to be changing dimensions due to any thermoelastic effect in space, then we're just going to be measuring the optical bench moving, not the gravitational wave signal. Because it's the ceramic, it has to be light-weighted to also, we're launching to space, so again, we have to keep in mind our volume and mass. And the first thing you can see here is this big blob here, which is called CAS, Constellation Acquisition Sensor. Not going to be talking much about it, but this is the very wide angle camera that initially captures the RX beam. It supports it's the very first coarse acquisition of the constellation. So, and this is provided by European Space Agency. And here we have the interface to the laser. The light then travels to this fiber switch unit, which allows us to switch between nominal and redundant lasers. It's just two half-wave plates that rotate when commanded. Then the light passes here to TX clip, which prepares the beam to interface with the telescope. We have point-ahead angle mechanism sitting here. We have beam alignment mechanism sitting here. The light travels into this beam and goes up to the telescope and to the far bench. Now, the same way we receive the light from the side to this periscope, and the light received and sent is multiplexed via polarization. So there is sitting the polarizing beam splitter, and there's a half-wave plate that allows to separate those two beams and sends the received beam here to its beam alignment mechanism, RX clip, into quadrant photoreceivers, so our eyes that look at the light and measure actually beat mode. In front of them, we have the imaging system, which on one hand shrinks the beam such that it fits into photodiode size, and on the other hand, it also minimizes effects from geometrical tilt-length coupling, as well as effects of iridiscs from the clip, which would reduce our contrast. Here is the B side of the optical bench. So now we're looking at the other side. The TX beam comes from the other side pops out somewhere here. Don't remember exactly. Here we have power monitors. They are part of the laser system. They measure and stabilize the power of the laser light, and they sit very close to the interface to the test mass. So again, this is the little periscope that shoots light out to the test mass, and this is due to the fact, what Honor already mentioned, those power monitors are so close to the test mass interface to ensure that we don't have any light intensity coupling to the test mass, to the noise. Then we also have, here are the fibers that receive lights from the adjacent bench and sends it back. So this is our LO. So this is optical. This is how the optical bench looks like. I don't know if there are any more questions.
What is tilt-to-length coupling? I always hear about that, and I don't know what it is.
That's a very good question. Can we wait for 3 more slides?
Okay.
Okay. So when you receive the laser light from the other spacecraft, it's extremely weak, right?
Yes.
But your local laser is very quite powerful.
Yes.
How do you compare the two then, without overwhelming the signal?
Yes. So there's a sweet spot, of course, and this is what we design optical bench for. So as you see, most of our light, go back to the A side. So actually, most of our light that is received actually goes straight out to the outside world. So we want to maximize the power that we send to the far spacecraft, and only the amount that is needed on our bench is kept and sent to other side and compared with the RX beam. Now, one thing is that I'm saying that there's a sweet spot because you're right, if we have too much power, then we just saturated everything and it's meaningless. But then also to a certain level, having higher power of TX enhances our signal. So it gives us this gain boost that we need to measure those heterodyne peak nodes in these powers.
So you don't necessarily need the two signals to be of the same...
No, that would be perfect.
Okay.
But yes.
A very practical question, like what is the size of a test bench?
It's 30 centimeters, more or less. So it's actually not that big, but it's pretty heavy. Yes.
You mentioned thermal expansion. I remember from talks about LISA Pathfinder that like it was operated at different temperatures. What kind of temperature is planned to operate satellites at?
So satellites actually have once they reach the stable orbits, are pretty thermally stable. However, we have to maintain guaranteed performance in temperatures ranging from 10 to 30 degrees C. However, we will have thermal stability on the optical bench of 5 microkelvin in band guaranteed from the spacecraft. So this is actually what we care about. We care about the overall thermal stability. This is not necessarily true to all the fibers, but yeah.
Okay, just to make sure. So when you say thermal stability in band, you mean
In the LISA measurement bands.
Temperature can vary, but only in lower or higher frequencies than we care about, right?
We care about the in-band thermal stability in the LISA measurement band.
Right.
Yeah. Okay. Any more? No, this is great. I love it. The key problem, or maybe not problem, the challenges of the building such optical bench was mentioned Pathfinder. Pathfinder only had one, and it takes very, very long time. It's very tedious. It requires precise bonding of the optics. There are 2 methods used here, adhesive bonding, which is mostly used for the lightweighting insets and combine it with the MOSA structure, but all of the optics is bonded via hydroxide catalysis bonding, sorry, which creates a thin layer of silica between the optic and the optical bench. Then the problem is that you have only 2 minutes to do it. After 2 minutes, it cannot be undone. So you can see the pressure on people doing it. For LISA Pathfinder, it was done by hand, but it's not practical because we have to build something like 10 optical benches, and they are both sided. So you can see already a little bit of an issue here. So what optical bench team, I should mention, optical benches are made in the UK. It's 2 institutes, UKNTC and University of Glasgow, that are responsible for this one. They developed a robot-assisted bonding technique, which is, I don't have a picture of it, but it's basically the robot arm that has a hexapod that precisely positions the optics. And then actually the rest has to be done by a human, but it already supports a lot of this technique, which had to be demonstrated because we're flying things in space. We cannot just decide that that's what we do. It has to be a qualified process. Therefore, they developed this is a breadboard that has lots of pads of the optics, and it had strict requirements how they have to bond the optics within those pads, and they had to demonstrate that they're able to do it over and over again and very precisely. And those are the results from the lateral alignment of the optical beam. So this was a big milestone that was presented during the LISA adoption, and one of the go-to, you're ready to build it. Now, I also mentioned that optical bench hosts mechanisms. Not going to be mentioning QPRs yet because they are part of the phase readout system, but we talk a little bit about the other. So first is beam alignment mechanism. There was a question about tilt-length coupling and tilt-length coupling compensation. So if you look here, we have 2 beams. One is well aligned with our detector and the other not so good. And then you can see if we have any jitter of the optical bench or MOSA, this is going to manifest as the phase change. That is not actually real, it just comes from the geometrical effects. We also have effects from the wavefront errors. They are not really correctable, so we only correct geometrical effects. So what BAM consists of is 2 optics, 2 plates that are rotated and give us the room to realign the beam to compensate for this effect. And there's a big team across multiple institutes that is working on coupling coefficients that had to be minimized and be able to apply the correct compensation. Not going to be going too much into details because we would be here all day. Second mechanism is point-ahead angle, as was mentioned. Our spacecraft, the light traveling between spacecraft is approximately 8 seconds, 8 and a bit. So we have to make sure that our spacecraft points into where the beam is going to be, where the satellite is going to be. And this is done by PAM. PAM is one-dimensional moving mirror, so it has this rotatable axis. And on one hand, it's just statically points to the far spacecraft, but also allows us to point the beam if spacecraft, due to any orbital effects, get out of a plane. So we have to account for that it can just move also in third dimension. So this mechanism being developed by the TNO in the Netherlands. The FMs are going to be provided by Germany, AI. And it has to guarantee low noise performance, as it is one of the components that sit right at the exit from the optical bench. Therefore, if it adds any jitter, then it's going to couple as the optical path length noise, and again reduces our ability to measure gravitational waves. Now for the redundancy, we have also those fiber switch units. Those are two wave plates, as I mentioned, and they rotate to allow to accept or send light to respective optical fibers, either with an interface with a laser or interface between two optical benches. This is being developed and provided by Czechia. Yes.
Is there another reason beyond just basically laser power that the two optical benches don't use the same laser?
Yes, there's also the frequency. So if we want to measure beat, we have to have different laser frequencies. And yeah, I mean, we could play a trick and have modulators that shift our frequencies, but they're not really low noise. So there's not really a better alternative than just flying many lasers. So all of those mechanisms that I just mentioned have to be controlled, and the whole control unit is being developed by Esron and Czechia, Esron in Netherlands and Czechia. And each of the front-end electronics that drive those units are being developed by either the respective countries, or in case of PAM, it's the same team as develops the whole unit, actually. So this unit just receives commands from onboard computer and tells PAM, for example, you need to move step to point to the right direction, or tells PAM, okay, now we have to do the calibration, and tells it to move. Same for FSUA.
Sorry.
Yeah.
How do these mechanisms know where the spacecraft is going to be?
They are told from the onboard computer.
Okay, how does the onboard computer know? Is it basically pre-computed orbits, or is it kind of measured?
So the orbits are computed upfront, and we know orbits for the very well. So we don't know them very well to large periods of time, but for I don't remember, is it months, 1 month, something like this? We know it very well, so we can know. And actually, the stepping of PAM is not really that often. Is stepping every day by the step is hundreds of nanometers, I believe, 200, and it's like few steps a day. It's really just a fine correction to maintain the power that we receive.
In LISA, in general, the timescales of orbital effects are out of band. Right? So you have to think that, it's roughly of the order of months, which is lower than the 10 to the minus 4 hertz that LISA can.
So I think when the spacecraft receives the beam, like the radius is kilometers, right?
It is, but you also lose power very quickly. So if we off point, the far spacecraft off points from us, so if we are the local spacecraft and far spacecraft off points from us, we actually lose power very quickly.
Can you repeat that? What's the diameter of the beam?
Hundreds of kilometers?
At the receiving end?
Yes.
Hundreds of kilometers?
Yes. I mean, you can calculate the divergence angle. So the beam is approximately, the diameter is 2 millimeters, and the optical bench is multiplied by 135 magnification of a telescope. So its waist is, around 30, slightly less than 30 centimeters, and then it has to travel 2.5 million kilometers.
Have you tried not doing that?
Well, then you would have to have a telescope that's the size of this room. Yeah.
It's a diffraction problem.
Yes.
The size of your telescope
Yeah.
drives the thing.
Oh, I see.
Yeah.
And the Ariane 6 has a limited size.
Yeah. So, I mean, yes.
So you need a bigger rocket, that's what you need.
You need to figure everything. Yes, and more fuel.
And a bigger check.
Okay, so now we're going to move away from the optical world and enter the electrical world. So let's check. Yeah, no, go ahead.
One other optical question. Like I heard in Euclid they had a massive issue that ice was building up on the mirrors. Is there like a similar issue that could happen in LISA? That basically somewhere ice develops and they had to reheat everything and like all these kind of things? Or is this like not a thing that can happen?
So we are on a heliocentric optic. We're not that far. But also we have the baffles around the telescope. So there is a big baffle, that big protection around the telescope. And actually telescopes are sitting a little bit hidden in the spacecraft. Okay. So they are not, when we always think about telescope, we need like JWST, which has this big mirror that is just looking at everything. And LISA telescope is relatively small because it has 30 centimeters, and it's just sitting snugly into the spacecraft because the optical band has to be 5 microkelvin, so it's well within the spacecraft. And only the secondary mirror of the telescope is close to space, and it's cold. But that's why it has the baffles that protects it and provides thermal isolation. Any more optical questions? Okay, so electrical world. So this is science interferometer, schematic of the science interferometer. We're not going to go to the big details here yet, but we have the RX beam incoming, and we have our TX. This is the combining beam splitter where we generate the beat node. To maintain proper redundancy in the science interferometer, we have four QPR, 4 detectors, so 2 on each port. Each of them sends the signal into LISA phase meter that actually extracts the phase information and provides other functions that are necessary for the constellation and TDI. So LISA phase meter is built out of 2 boxes, roughly. The reason is very pragmatic. That bit is very sensitive to temperature. It has analog electronics and analog digital converters. And that bit consists of power supply unit, and they don't like each other very well. So first bit is our eyes, is the LISA quadrant photodetectors, which we call very often QPR. So if I say QPR, it means detector. It's shown here. The quadrant photodetectors are developed by the ESRON in the Netherlands. So Dutch Space Agency is the lead agency, together with NICEF, that is responsible for performance, and KU Leuven for front-end electronics, so the amplifiers, and et al. So the QPR, the quadrant photoreceiver, transfers the optical beat node into the electrical photocurrent. And then it takes electrical photocurrent, amplifies it, transforms it into voltage, and sends it to the phase meter to extract the data. Why quadrant photoreceivers? Because we want to measure DW signal to support the DFACS, so spacecraft attitude control, which Henri mentioned in his talk a little bit. We have very stringent requirements on the performance of those QPRs, so you can imagine, like everything in LISA, it has to have very low noise performance and high responsivity. It has to cover very high dynamic range of the signals, so from the very tiny beat nodes in the science interferometer, so pretty strong beat nodes in the reference and test mass interferometers.
Sorry, I did not understand why 4.
Sorry, why 4 quadrants?
Why 4? Why a quadrant?
Yes. So, very good question. So, why 4 quadrants? 4 quadrants basically create 4 diodes. So, they have the split, and we have the segments as it's shown here. And what does it mean that we measure independently each channel, as it's shown here, right? So, we have each channel is measured separately. And that allows us that if we take the A, B, and CD and subtract, and the same AC and BD and subtract, we directly can measure the phase lag on those quadrants. So let me retract back. So we have two wavefronts falling on this photoreceiver. One is the RX, the other is TX. And if one is tilted with respect to the other one, we're going to see advanced phase on this side and retarded phase on that one. And this is the signal we're going to measure. Now, if we subtract it, we're going to measure phase difference across those quadrants. This is directly proportional to the angular misalignment between those beams. That's being fed to DFACS, to drag-free attitude control system, which now can tell, hey, we are misaligned. This is combined together with the sensing from TESMAS and corrects the spacecraft position.
Wow.
Is it answered?
Wow. Okay.
So now, we covered the photo receivers. Now, we need to send our information further to the phase meter. And the first unit is called interferometric processing unit. It consists actually on two modules. Here is just the one that extracts phases. It also has another module that deals with clocks. If you have any questions about this module and clocks, I will direct you to Sergio. He can tell you more about it. And this is how those boxes look like. That's standard space electronics, very robust, needs to survive the launch with just the connectors at the front and back. So let's jump to the interferometric processing unit. It receives the signal from each interferometer and reads the signal, extracting our phase information. Its frequency distribution module distributes clock to the laser, so interface with the laser. I'm going to talk a little bit about clock sidebands in a second, and more tomorrow in Olaf's talk. It also receives the PRN code and extracts it, and supports the beat node acquisition by tracking the beat nodes and tracking the so looking up for the beat node. So the one thing what I would like you to understand is the basics how phase meter works. So bear with me because there's going to be a little bit of math as well, but very, very simple. So the core of the backend electronics or the phase attraction system is phase lock loop. Phase lock loops are pretty standard things that are used all over the places. We have digital phase lock loop because it's in a digital land of the phase meter. And the non-standard thing about it is what I already mentioned. It has to cover a very large dynamic range. Not due to power, but due to all of the orbital effects, and that we have beat node from 5 megahertz to 25 megahertz that we have to cover. It has to provide very high precision measurement, and it has to measure instantaneous phase from each segment of a QPR. So we have 4 of the DPLLs for each quadrant, and they subtract the longitudinal measurement, this is the scientific one that we really care about, and the angular measurements, and then also ellipticity of the beam, which is critical to later backtrack. So let's jump a little bit to how this works. I just need some water. If there are some questions, there's a good time for that. Nope.
Maybe as a order of magnitude, say dynamic range, maybe just to give ideas. Yeah.
So I get a little bit more water.
Yeah. Yeah, just to give ideas. So the beat nodes are between 5 and 25 megahertz, and we cannot make them fixed because of Doppler shifts of the orbital effects, right? Mechanics. And we need to measure nanoradians, which in terms of frequencies is about 10 to 100 of nanohertz. So we need to measure tens of nanohertz over tens of megahertz. That's
Yes.
roughly the range.
Thank you. So let me jump forward. So as I said, at the front here we have the signal conditioning electronics and analog digital converters. So they receive the voltage signal and they transfer it into digital land from the real voltage land. So our input signal to our phase lock loop can be represented like this. This is the digitized signal. So it shows, so it's this instantaneous, and it has, so the frequency here is in cycles, in the units of cycles, and a phase in units of radians, and they depend on this quantization n number, which represents, so the difference between this signal and the signal now that arrives at the time n+1 is 1 over sampling frequency. So later in post-processing, we'd have to reverse it to get back to hertz and actual phases. So right now, we are in this phase meter digital land that operates on its own units. So here we have the input signal, and this input signal is being multiplied with sine wave and cosine wave that is copy of our signal. So it has the same frequency, but it has different instantaneous phase. Now the product of this multiplication is on one hand value that we call I, which is in phase or in phase component, which is directly proportional to the amplitude of our signal. This is not really of interest for the scientific meaning, but it is very important for us to say if something is happening with the QPR in this particular segment, because that we can say, oh, the powers, something is wrong here, and then we can use those values to correct or mask the segments that are failing, for example. So this is quite important for us for further maintenance and debugging. Now, what is of our interest is called the Q, or in quadrature component, and it's directly proportional to our phase. So if we mix those two signals, we are getting something like that, which has this component of sine wave, which is proportional to, has this term of phase of the incoming signal with instantaneous phase of our copy of the signal. And then we have this component that is 2f. And we want to get rid of that one because that's not of our use, and therefore we have this filter sitting here, and this filter ensures that we cancel out this term. And we are left with the error signal that is proportional to this phase difference. Now we feed this signal to our servo, and our servo ensures that this Q value is always at 0. It always wants to do, the only thing it wants to do is want to make sure that our Q value is close or at 0 exactly. So the output of this controller is going to be a copy of this our argument, right? And this is being used to feed to our back to our sine and cosine copies and back to close the loop. So this is running in a loop, and it's instantaneously you receive the signal, creates a copy, sends further, creates the copy, sends further. Now we have also two bits sitting here. One is P phase incremental register. It takes this phase, this phase that it received, and now if we think about it, we have this term, this copy of our instantaneous phase, and if we multiply it by 1 over f sampling frequency, we receive directly something that is proportional to our frequency in hertz. So this is actually signal of our scientific interest, and this is directly proportional to our frequency. Now, further is sitting the register that adds everything it gets from this PIR, it accumulates it. So just keep on ramping, keep on ramping, keep on ramping. And this is directly proportional to the measured phase. And those two signals are picked off and sent further as a scientific signal to the next unit. So here we have 3 signals, Q value, which is driven to 0. You would think, like, why would you measure, why would you want to know 0? You want to know 0 because if it's not 0, it means that something is wrong, and we are not having valid signal. We have to make sure that this is not going to get to scientists because something is wrong, and we have to debug system. Those are of scientific interest, and this is, again, as I mentioned, is our debug system. Okay, are you still with me? I promise now it's going to get easier, somehow. The first problem that actually Olaf is going to be talking about, I think, tomorrow, right? He's going to be talking about that, for sure, is that our ADCs at megahertz are not that good. We cannot buy off-the-shelf component and measure the phase really well. What we actually get is that they have timing jitter, and they don't sample evenly. They sample a little bit off, and what we are getting is this. And see, like, okay, then we cannot measure our signal. So to play a trick and correct this error, we take our known common frequency, we distribute it to every backend electronics, so every ADC that is measuring. And in post-processing, in the second unit that I'm going to be talking about in a second, we correct it, and then we get our signal that was that we wanted to measure. So this signal has to be very well related to the master clock of the spacecraft, and it has to be very well related to the sidebands that we exchange within the constellation to use in the post-processing. So this is very, very important and key, one of the key aspects that we have to keep in mind when we are building phase meter. Now this is also something that Olaf is going to be talking about. I'm just going to very swiftly skim past it. So, as I said, we have to exchange time between spacecraft, and this is also done by this unit. It generates the gigahertz sideband. It sends it to our laser system. Laser system consists of the electrical optical modulators. It modulates this gigahertz sideband and sends it to the far spacecraft. And what far spacecraft is going to see the offset peak in its frequency space, and it's just going to measure the frequency difference. And phase meter doesn't correct anything. It's all done in ground on post-processing. It just measures this difference. So more on that tomorrow, I believe. Now the second unit, the phase meter control unit. It acquires scientific data from the interferometric processing unit. It corrects do this piloton corrections, combines our QPRs, because we have 4 in science, for example. So we have to combine into one signal, and we send it to onboard computer to be ready to package nicely and send to ground for post-processing. It also provides transponder log, which is very key function of the constellation. It provides the PRN modulation, so it modulates PRN code onto the laser system and reads it. I'm going to just show briefly something about that. And as I mentioned, it interfaces with OBC, so it receives commands and sends commands to the OBC. Not sends commands, sorry, receives commands and sends the data and information what it required. So now the key, another key functions that we need for TDI is the absolute distance between the spacecraft, and we need to know it within approximately 1 meter. Again, what we do is we have known copies of our pseudo-random code on each spacecraft, and what phase meter really does, it only reads this code, compares it with its local code, and it looks if its code arrived earlier or later. And it just compares it, is it earlier, is it later, measures this delay, sends it on ground to post-processing. So it doesn't do anything with it. And I don't know if there's going to be a little bit more on that, but this is one of the key TDI functions.
I might have missed this part here, but you don't have any auxiliary channels in LISA?
No. I mean, all of the QPRs are directly powered into the phase meter.
Okay.
If we lose channel, we lost channel.
Ah.
That's why we have 4 QPRs.
No. Oh, I see. Okay. But even for like other estimations, like you don't use another kind of laser at a different frequency. You don't power all these other stuff. Like
No.
LIGO has a bunch of other channels just for like noise subtraction or like just to understand the noise or maybe phase and stuff like that. But I guess you don't. Okay.
Yeah. I'm not sure, very sure. So we have 2 lasers on each optical bench. And if there's any problem, they switch. But they never work in parallel.
Okay. You do have a bit of redundancy with all the sensors around the test mass, let's say electrostatic sensors. So, yeah, there's kind of redundancy for that. You have also, let's say, the electrostatic sensors around test mass that are not used for TDI, but they can help also to understand how the test mass move inside the vacuum, the housing and stuff.
So you can use it during some bleach, right?
Yes. Yeah. Oui.
And there are other sensors, right? You measure temperature, you measure like.
Yeah, we measure temperature, voltages. We just monitor everything. Yeah. So basically, our science data is like really peanut compared to everything else that we measure to make sure that it works.
Yeah, we do. Like LISA Pathfinder, everything that was done with LISA Pathfinder, or like most of the things could be theoretically done with LISA, with the caveat that the measurement is more complex. But, yeah.
Okay, so now I wanted to talk a little bit about the noise. This is just to show you what kind of requirements we are facing in the interferometric detection system. We have the noise floor of 9 picometers, so we cannot add more than 9 picometers. We have a noise floor of 2.1 picometers and 2 picometers respectively in test mass and reference interferometers. And we also have quite stringent requirements on DFACS readout to make sure that the DFACS system works properly. So,
Can you just explain DFACS?
Drag-free attitude control system that controls spacecraft attitude and positioning. Thank you. So this is just a very top overview of what we budget for and what we know and expect noises in our instrumentation. So you said this is just to the first level. I don't want to go into too deep details. But as you said, we have the 9 picometers, and we have the thermo-optical effects from the optical bench. We have the noise, in-band noise generated by the QPR that's usually related with the self-heating of the analog electronics. So we have to make sure that this is under control. We have noise coming from the phase meter because it doesn't work perfectly. Also, it works on the weaker the beat node it measures, the harder it works, and unfortunately adds more noise. We have to cope with the stray light that comes from the telescope. Therefore, we use this balance detection. So we have 2 pairs of the QPRs. We have to deal with the RIN noise of the laser, and we try to suppress it by using balance detection to the large extent. Although there is some trade-off between what we compensate stray light and RIN, and which doesn't give us 100% of the reduction in noise. And we have to leave with the shot noise, which is also a fundamental light noise. And this is how it looks so far. This is our requirement, and this is all our contributors as we expect and as we predict. So we have, on one hand, we have allocations that were hard deadlines. You cannot go further than that. And we have our estimates where we can tell, okay, we think at this point we are here. The more we measure, we test our equipment, or we model better our equipment, better predictions we have what we actually expect. Then we have similar for the test mass interferometer. Here the caveat of the stray light is that we actually have quite a bit of stray light from the backplane. So the fibers reflect the light that goes in to the backplane, back to the test mass and reference interferometers. And we have to ensure that we suppress this noise. They also trick that we play by having quite a large power ratio between those beams to ensure that we don't soak ourselves in noise in those interferometers. And this is quite similar for the reference interferometer. It suffers the same noises as the test mass. Not going to be going over it. Wanted to briefly show you that.
Can I say one thing?
Yes.
For people who don't know much about the instrument, this is quite important. This is called, this is a noise budget or noise tree. And this is when all the instrumentation people look at all the systems and try to pinpoint each noise source. And each of the blocks you see, they form a tree, right? Where the uppermost block is the sum of the next level and so on. And Ada said it, you have two ways to go. From your science requirement, you say, if I want to measure this, it means that on the topmost level, I have to have this noise at most. And then you budget, you kind of, assign the noise to the next level and so on. So that's what Ada called allocation.
Yes.
And you can go the other way around, say, I have experiments, I test my stuff. This is my best estimate of what the noise levels of this block is. Then I sum it up, I go up, and hopefully, in the end, you should be below the allocation.
Yes. So this is, thank you. This is our benchmark also for our verification. So we always verify against this requirement, this allocation, that we need to be below. Otherwise, we have to scream higher and say like, hey, we're a bit violating. And then hopefully we have so-called margins. So we get the requirements from ESA. So we have science requirements, right? This is what we want to measure. Therefore, we have mission requirements, what our mission should meet. From there, we have requirements to systems. From there, we are the system, so we have to give the requirements lower. And those little boxes represents those requirements, and in particular, those little allocations here. What to say, alloc? I don't know if that's very visible. And then our equipment measures against it and say, hey, we are meeting our requirement, and we're all happy. And they say, hey, we are struggling. And then either we have margin and we say, okay, we can give you a bit more. We're still meeting our requirement. If we don't meeting our requirement, we have to go higher and say to ESA, like, hey, we are not meeting our requirement. That goes to performance and operation teams. They assess and they either say, yeah, you can violate it, we give you a bit more, or no, guys, you screwed up our, hopefully not. The sensitivity is not going to be reached in a certain allocation. So this is very important for us. This is actually key. Our work is ensure that we really meet those requirements and we really meet those allocations. And this is a huge work of a lot of people to ensure that we're building the observatory that is going to perform as we want it to perform.
And it can be a fight, right? Because if you struggle to meet the requirements, it means that it costs money for the people responsible for this subsystem. And so, it's a fight to say, we're not struggling, but hey, maybe assign, part of my requirement to my neighbor.
Yep. And in particular, because we are all closed system, we can screw up GRS by putting too much power on them. They can screw us by scattering too much light from the window to us. So we had to work very carefully with all the teams. We're in constant discussion, for example, with NASA colleagues, because we need to ensure that we are having the right interfaces, and it's very, very, very important. Lots of documentation, though.
Do you interact much then with the whole figure of merits idea? So the idea that the linking directly from the hardware to the science objectives?
Yes, so between us and the science objective is the performance and operations team. It is chaired and head by ESA, and it spreads along many, many institutes and reaches out to the other side of the pond. So this is a huge collaboration of people to ensure that this works. And what we are getting from them is those requirements, and then we assess them together. I mean, it's not like they give us, like, this is yours. We sit together, we assess it, we say, this is reasonable, this is not reasonable, we have to, you know, but our goal is to really meet the science objectives.
Okay, thanks.
And to do that, we have to verify. This is a backlink interface experiment that is being a joint venture between University of Glasgow and AEI Hanover. If you have more questions, Georgina, there. She works on one of the connected experiment. So to measure this backlink, we have to have 2 optical benches. This is kind of unrealistic because it's very hard to build them, as we discussed it, and just having 2 for the test is very hard. So UKATC and University of Glasgow developed this optical bench that mimics all of the bits of real optical bench that are relevant. We have those backlinks. So it's basically, if you split this bench into 2, you have one optical bench and the other optical bench. And we need to verify that we meet our noise allocation. And the setup for this measurement is being developed by AEI. Here's a shiny picture. This is a shiny picture of our mock-up that we use to test our equipment. It's built out of metal, not the zero-door, like a real bench. But we developed it to test our readout equipment. And there is another experiment that Georgina is working on, which is free backlink. It actually was earlier experiment delivered to test different options of this interchange. So it has 3 different links. And yeah, if you have questions about that one, please find Jordi. And now the second important thing, I tortured you a little bit with the phase readout system and DPLLs. We need to ensure that our readout system really works, right? And works as we expect and provides all of the functions. For that, we are developing a dedicated test setup, which is called Hexagon, because it has 6 beam splitters and try to mimic 6 links. Such that we can exchange PRN codes, we can exchange timing signals, and actually verify that everything works within the noise level that we allocate. So this is schematic of a setup. I'm not going to go to too much details, so we make it to lunch. But this is the shiny picture of how this bench actually looks. This is how it was built. It was built at AEI by students and postdocs, PhD students. And I don't have the measurement, but it meets our requirement, so it was, I can say, well built.
Maybe something stupid, but everything looks transparent. But Lisa uses infrared lasers, so actually mirrors are transparent enough that like visible light, but not in
yes.
infrared. So there are mirrors here.
Do you? Sorry, I'm taking advantage that I have this. Do you do verification like after launch as well, like to make sure that everything's still working okay, or is that built into all those kind of checks that you're describing?
Yeah. Yes. The answer simply is yes. But so we are responsible to verify on ground as much as we can. Of course, we cannot because we don't have 6 links. So we are trying to mimic all of the verification that we can do before we deliver to a spacecraft. Once it is delivered to spacecraft, we still support with a lot of verification. Once it is launched, it is actually performance and operations team responsibility to verify. A lot of us from hardware is part of the performance and operations, and we together will work on developing those tests. But it's not yet fully defined. So we have 1.5 years in transition, and then and commissioning. So it's not going to be like we turn on the LISA and we're going to get data yet. We will have to commission, check everything, and make sure that we acquired everything.
And will that be done in flight as it's getting to its Lagrangian point, or you wait till it's there and then start verifying?
So LISA is not in Lagrange point. It's on the heliocentric orbit. It just lags Earth.
Ah, okay. I thought it was like L4 or something.
L3 It's very confusing because very often ESA says like, oh, our L3 mission. It means large mission 3.
Yeah, it's 3. Yeah.
It confused me as well at the very beginning. So during the transition period, we can already test a lot of systems. We can turn on the local laser, but we want potentially, I mean, it's 2 watts, so if it doesn't go out, then it goes somewhere, and that's scary.
Okay, some, not all.
Yeah, but some things are going to be tested because we have to monitor the temperatures, we have to monitor behavior of the even turned off equipment.
And have you been allocated a time once it's in position to, like, how much time you guys have to verify? Just because I know there's all this stuff about data being released within a certain time and stuff. So
I believe there is, but it's, as I said, it's a little bit more to ESA and Prime to decide because there's going to be tests of spacecraft. So it's not only so we are delivering the so-called scientific payload, and then there's a whole spacecraft around it. And it also has to be verified that all of the functions work. So there has to be probably very tight schedule, but we also need to make sure that we start observing. We don't want to test equipment for 2 years.
Yeah.
So, but we will have to make sure that we are delivering the right thing.
Yeah, thanks.
The big test campaign that we plan for this whole interferometric detection system is actually being developed by CNES in Toulouse with a lot of partners. Not going to be going into too much detail, so I'll make it to lunch. But they're developing a whole facility that will host all of this optical bench, all of the electronic boxes. They're being developed special phase meter ground support equipment for this test. And it's a huge campaign, and this might be interesting for some of you who work in data processing because that's the data, the most LISA data we're going to get as a noise measurement. So this is how it looks. How looks the whole setup? Just to show you bits and bobs and the magnitude. The APC develops whole bench that mimics the adjacent bench and the far spacecraft for this measurement. This is a big effort of many scientists to build it. And these are all of the scientists, all of the institutes, because it would be very hard to fit all of the names here. They are working on to making sure that we deliver the payload. And here I wanted to show you a few spacecraft pictures that I'm allowed to show. I think the first 2 were actually on LinkedIn, so...
Yes, of course.
So you already saw that one?
Yeah, okay, that doesn't work.
So this is how the LISA spacecraft is going to look. This is the rendering from OHB, from our prime contractor. This is the radio antenna. There was a question how we talk to LISA. That's this high gain antenna. You're going to see in a second, telescope is hidden here. And this is how all solar panels are unfolded and gather energy from the light. This is how the MOSA looks like. So you see this is the baffle that protects the telescope. Gone.
Oh.
It's like a small car. And here how it is stacked for the launch. So those solar panels are flat, covering everything, and this is the stack of the LISA for prepared to go.
Do you know what else is being launched?
I don't think anything really.
Yeah, one thing.
Is it?
Yeah. There was this first launch for Ariane 6.
Doesn't have a question, so it's too late.
Okay. Are there any more questions? Yes.
What is the estimated power consumption of one of these satellites?
No idea, to be honest. Is it 10 watts? Okay. 10 watts.
So what prevents? Okay, this is again probably money, but like what prevents you from having more solar panels, like a larger array?
Size.
The size. You can't fold it up, like how JWST's been folding stuff up. Oh, this is already folded
It
up.
took 15 years for GWST to be able to fold its mirrors.
I see.
Okay. Okay. I hope it was somehow fun. Thanks a lot.
Any more questions? We have a bit of time for maybe one or two questions. I think questions were asked.
Yeah.
I have a quick one though.
Yeah?
Oh, I think he has one, but you haven't asked a question.
So about the specifications of the laser sources, what kind of lasers are they, and
So
what
those
kind of
are
requirements?
so-called micro and pro lasers. I don't know if you're familiar with the N-Pro laser that is used in LIGO. So they actually very much shrink. There is two. So there's redundancy upon redundancy, and I'm trying to think. So there's two heads per optical bench, 3 amplifiers. They are interconnected. And yeah, I don't know what else. What would be of your interest? What exactly specification?
So like the type of the laser?
So N-Pro, so this is the solid state laser with the crystal oscillator. So it has the pumping diodes and that pump the crystal. Sorry. And behind it, to reach this 2 power level, is actually the EDFA amplifiers. So erbium doped fibers. Is that answering your question? I can produce more information, but
it's 1,000 and something nanometers.
1064, yeah, plus minus 0.5.
Hi. So the 3 telescopes aren't physically connected. So say if one were to be impacted by an external object, how would it correct itself in order to continue to take data accurately?
So you're saying when we have the impact on the spacecraft,
yeah,
we have micrometeorite that hits it.
Yeah.
Yeah. So so first thing, if we have any micrometeorite impact, the spacecraft is going to move, right? And then because we're in space, it's going to continue moving. So what we as our system have to make sure that, one, we maintain laser lock. Because we are having, as Henri showed, cascade of lasers locked to each other. If one at the beginning loses lock, then we lost the constellation and we have to start over again, and we are down for who knows how long, because we have to turn on CASP, we throw thermal stability of everything. So what we need to ensure is that for very, very tiny signals, we still can maintain lock. We're not maintaining science anymore. We just sit there and try to ensure that the constellation is still in lock. Then we also have to provide valid DWS signals. So we have the requirements on the range, and we have to make sure that we provide valid signals to DFACs, such that DFACs can react and quickly start correcting the course to get the satellite. At the same time, what we do, what phase meter does, it raises flags and says, I'm in trouble, I'm not measuring anything meaningful, I'm just trying to work. The details are not even worked out, but it might release the gains on those tracking loops to make sure that it's not meeting performance, but it's just keeping track of everything and it doesn't lose the constellation. Is that answering your question?
Yeah.
DWS is the differential
waveform
sensor.
sensing.
That's these thing where you measure
the angular,
yes, in the beams with the quadrants.
Yes.
Yeah, so you have 2, one per telescope, and then you can with that measure the attitude of the spacecraft. And there was black meteorite that he studied, the spacecraft knows that it was tilted, and that corrected back.
Of course, if you too quickly, then you lose constellation locking. And
then we have to restart everything, and then we start the process of a constellation acquisition.
And what kind of like systems do you have in place to protect against space weather or like different phenomena from the sun?
So this is more question to people who are choosing the orbits. They were tasked with choosing the orbits that are very quiet and provide us with the good conditions. As we know, there was, for example, a problem with JWST in the first months of launch because they thought that it's going to be very quiet and was hit by a very large meteorite. I mean, not very large, it's still micrometeorite, but larger than they predicted, and they got in trouble and it damaged quite a bit, I think, of solar panels. So there's things that we cannot predict, but the choice is where the satellites are, really, because we cannot do anything else. There's maybe one thing to mention that the telescope will get damaged over time. Right, so the quality of the primary mirror are going to get scratched because something can hit it. It's going to get dirty. It's going to degrade in performance. And what we actually work is with our requirements is to end of life. So our goal is that after the science allocated time, we are still measuring the performance. So we're not, targeting the beginning of life when everything is not new and shiny. And then after 3 years, no, it has to be done. The work has to be done for the end of life. So, yeah.
Thank you.
And maybe a last thing about this, it can also look like a signal if you have the system calibrated enough. For instance, this tilt-to-length coupling. If you get hit by this micrometeorite and it gets a tilt, and then it propagates through the long arm, and you could not correct that properly, it can look like a signal. So you need also to take care of that.
All right, let's thank one last time Ada.